Welcome to the segment on page replacement. Last time we looked at virtual memory and what's its use. Today we're going to look at how to manage virtual memory as a resource, how to manage memory as a limited resource, and how to be clever about figuring out which memory pages are important and making sure we keep them in memory, and which pages are not important and throwing them out when we run out of memory. So the fundamental idea behind page replacement is this notion of demand paging. We already looked at part of that, I was giving you many hints as part of the talk on virtual memory. So what is demand paging? Okay. So in general, modern programs require a lot of physical memory, but they don't really use all of their memory all of the time. They normally, in systems, there's a 90-10 rule, which says that 90% of the time is spent in 10% of the code, right? So it's very wasteful to require all of the user's code to be in memory, right? So if you load the whole program in memory and keep it all around, then most of the memory that the program needs is actually really idle. So it's not really being useful. It's stored, it's occupying memory space, but the program doesn't really access it that often. It just comes and accesses it ever so often, right? So in such cases, uh, it would be bad to maintain it all in memory. Okay, so the idea behind virtual memory or demand paging is that the solution is to transparently maintain the memory pages between disk and main memory. Okay, so you constantly keep moving back and forth between these two using your page table. Okay, so the technique trick we're going to use is we're going to use the page table to point to whether the page is in disk or memory and constantly keep moving between those two when we run out of space. So when we have unimportant pages, we're going to get the page table to point them to the disk, and when we have important pages, we're going to get them to point to memory, right? And when we want to transition from unimportant to important, we move from the disk to main memory, and we swap it out to disk if it's unimportant. Okay, so I just wanted to make sure that I clarified that the 90-10 rule, while in general applicable, is not necessarily true for all programs, and in fact is not true at all for most recent programs. Most programs a lot of important programs we look at today. For example, things like web servers. So web servers spend a lot of time, equal amount of time on each piece of data if you assume that the data accesses are randomly distributed or uniformly distributed. Okay. And if you look at things like iterators over things like graphs, where you're touching every data element, doing some little bit of work on it, or computing something at every node, then again, this 90-10 rule doesn't apply because you spend a lot of time accessing different all the data elements in your data set. Okay. Okay. So the general idea behind, so what I'm going to do is talk about the technique and the illusion of infinite memory in general, and then I'm going to talk about the specific algorithms that we're going to use to transparently move pages back and forth between physical memory and disk. Okay, so virtual memory is what your program sees. It's directly related to how big the number of bits used by a program. If you have 32 bit space, then you have 64 gigabytes of address space. If you have 64 bits, then you have 16 exabytes. All of this memory has to go through this combination of TLB and page table, right? So anytime you have an address that is accessed in virtual memory, it has to go through these two components, these two gatekeepers. Okay, these two gatekeepers then for each page they really have pointers, right? So they have pointers that can either point here to the disk, or they have pointers that can point to memory. If it's pointed to memory, then the page resides in memory, and then the application can immediately access the page. If the page resides on the disk, then it does a swap in from here. So first step, it figures out it's on the disk. Second step, moves it from disk to memory. Third step actually does the data access, right? So it follows a three-step process if the page is swapped out to memory disk. Disk in general is larger than physical memory, and this is not always true. Again, modern systems try to over provision. Um, Disks in general are larger than memory, but really what you do is you don't allocate the entire disk. What you do is you vend out a chunk. Okay, that chunk is what's known as swap space. So swap space is the space on the disk or the chunk of memory on the disk that you're going to transparently use to constantly move memory pages from physical memory to disk and back when you run out of memory. Okay, but in general, in-use virtual memory is bigger than physical memory, and disk is larger than physical memory. Right? So the basic principle is transparent level of indirections. So what this does is it supports flexible placement of physical data. You don't really care about the actual storage technology, right? You could be placing on the disk, on memory, sometimes even on the network, as some systems do. Like systems like Facebook, for example, use big hash tables, and these could be scattered all across the system. So when you make an access, you figure out which machine it actually lies on, and then go get it from there, right? And it really makes the location of the data completely transparent to the user program, which is very beneficial because the runtime can then choose to optimize it in different ways. Okay. So demand paging is a form of caching. Fundamentally, what you're doing is making sure that important data lies in fast storage and unimportant data goes back to slow storage. So there are a number of questions, if it is caching, that we need to answer. For example, what is the replacement algorithm? How do you figure out, how do you pick an allocation candidate? Do you allocate more memory for a program, or do you, start swapping out pages? So there are a number of questions that need to be high-level design decisions that need to be answered. And I will also use this opportunity to distinguish memory to disk versus cache to memory. Okay, so you have CPU caches that are low latency as well, and if you think about it at the high level, this cache to memory relationship is what memory to disk is. But there are important um, design decisions that highlight some important differences. For example, hardware caches or CPU caches are maintained entirely in hardware. We'll see why that's the case. Okay. So first is, what is the block size? Okay, so the block size is normally a page. So why is it a page? So it's a page because, for one, you can overload the virtual memory system, which understands pages. For example, page table entries are all at page granularity, right? So can you overload that to essentially implement demand paging? Right? So that's one of the reasons why it's page. The other main reason is that it's the more important reason actually is that when you have things like disks, which are slower technologies, you want to transfer a lot of bytes at any given read so that you can amortize the cost of a read itself. If you read a disk byte by byte, it's going to be really slow. So what you do is you split it into blocks of size. We'll look at disk blocks in more detail later, but essentially things which are page granularity, and then you read an entire page at a time, right? So if you want to search for the page in the cache, when to look for it, you check the TLB, check the page table, and the replacement policy is, what is the replacement policy? No space in memory, so you could use LRU. We look at a lot of them because it's kind of LRU, but it's not exactly, because LRU requires a lot of overhead to run, to implement, and we look at approximations of LRU. Okay. And what happens on a miss? So you refill from the disk, and if what happens on a write? Writes are particularly important because there are two forms of writes that demand paging normally implements. One, or any form of caching needs to think about. One is write through, and the other one's write back. Write through is a system where if you've got one level and you've got a bigger level, memory to disk kind of, write through is all writes go through. The benefit is that anytime you replace something from here, you can just drop it on the floor because all writes have gone through. The data is completely synchronized between these two. Think of it like a Dropbox system where it's completely synchronized between the level 2 and the level 1. Right. Write back is when you don't have that, and writes really happen are stopped at this point. right? And then once in a while, based on some clock or some algorithm, when you run out of space, you you swap, periodically back to the level 2, right? So this is write back, the other one's write through, and every write goes through. Okay. So if you want to write back, then you need to figure out which pages are dirty as well. So a lot of the design decisions are also made, based on performance as to what are the important criteria. Not all of these are equally important, right? So for example, replacement algorithms are really important. We'll see what is the goal of the replacement algorithm. Is it to maintain important pages in memory, or is it to make sure that it knows the truly useless page to be moved to disk? These are two extremes. Right? Figuring out what is the most useless is very different from figuring out what's important. Okay. So demand paging, like caching, needs to compute the average access time. So the average access time, right? Okay, that's the average access time, is a function of both the hit rate. How often do you stay in memory, and how much is memory latency versus how often do you miss, and what's the miss latency. So memory normally runs in the 200 nanosecond category, and an average page fault is 8 milliseconds. Most of this is just finding the page on the disk. So disks, what's known as disk seek. We'll look at disks in more detail, and as part of that, I'll explain this. So you have some probability of miss, which means the hit probability is 1 minus p. So the estimated average time is 1 minus p into 200 nanoseconds plus p into 8 milliseconds. Okay. So if you assume that, um, so if you assume that this is really small portion, then what's really important is this, right? So the general idea is that, let's look at some probabilities, right? Let's say that 1 out of every 1,000 accesses causes a page fault, right? So 1 out of 1,000 is something like 0.1%. At that point, you're already seeing an 8.2 microsecond average latency, a 40x slowdown compared to versus memory, right? If you want slowdown, so you don't want to, obviously you don't want a 40x slowdown. So the question is, let's work backward and say, let's say I want to slow down at only 10%, right? Then essentially the probability would work out to something like 1 fault in a 400,000. Right? This is the important challenge of demand paging and page replacement algorithms in general. You cannot err on the wrong side. You can always replace a page that's less important. That's okay. But don't ever replace a page that's really important. So you got to make sure that you know absolutely what's important, right? Because if you replace an important page, the penalty is way too high, and you don't get that many chances to um, make corrections or get it right. Right? Only 1 fault in 400,000 is all you can afford if you want to achieve only a 10% slowdown. So if misses are really that important, then the question then becomes, what can lead to misses, right? So back in the 80s, there's this person from Wisconsin, he was a graduate student at Berkeley called Mark Hill, who published this 3C policy. Okay, so there's compulsory misses, which is essentially the first accesses to new data. Right? This you can't really do much. But better management policies, no, it's not going to make a difference because it's the first time you're touching the data, and the only way you can avoid it is if you kind of predicted the future, right? I knew exactly what you were going to touch ahead of time. So prefetching is a standard strategy that's used. Normally, people prefetch sequential things. So if I touch some piece of data, like in a file, I kind of bet that you're always going to access the next data on the file as well and bring that all in at the same time. Capacity misses is when there's not enough memory. How to increase the size is the important question, right? So I don't have enough capacity. So again, here you can't really do much other than just putting in more memory. Or you can, kind of, there's interesting, you can use virtual budgets, right? Where each process gets a certain amount of memory and you dynamically control what each process gets. Okay. Finally, there's policy misses, which is our primary interest in this case, which is, you have pages in memory and you kind of kicked out prematurely the important pages. Right? This obviously we can try to solve by better replacement policy and trying to be really clever about what data is actually maintained in memory. Okay. So the reason we care about replacement is the cost of being wrong is really high. And if you go to disk even 1 in 400,000, you're already seeing a 10% slowdown. So the goal is must keep important pages in memory. Okay, the goal is not to figure out the least important page. Is to figure out what are the most important pages and make sure they keep it in memory. Okay, the simplest algorithm would obviously be random, which is normally what's used for hardware caches. But this is really unpredictable and makes it hard to provide real-time guarantees, which means operating systems do not use it. So random, not used. Right? So actually, random is not used in operating systems. Okay. So what we're going to do is start looking at page replacement algorithms. Before that, I want to kind of refresh you back to what a page table entry is and talk about all the information in page table entry, so that some of these are going to be useful for replacement algorithms to figure out which pages are important, and others are just used for implementation. Right? So page frame number essentially is the one that's going to either point to disk or it's going to point to memory. Right? So it's the one that's implementing the demand paging mechanism. Okay. There's a present and absent bit. One if the page is in memory, 0 if it's not. So this one figures out that the page is actually on disk. There are protection bits. Obviously, these are not useful. These are mostly for security purposes. And then there's the caching disabled one, which is usually used for I/O purposes, and we won't talk about that. But there are two important ones, right? The two important ones we want to focus on is the modified and the reference bit. The modified bit says the page is written, right? So which means that if in a write-back system, moving the page to disk is going to be really expensive. It also possibly indicates a level of importance. Okay, reference bit is set when a page is read or write. So essentially, it tells you that the page was read or written in some time in the past. Right? How much longer in the past? That the system has to figure out with some clever techniques. But both M and R bits are useful for our page replacement algorithm. So let's look at what they mean in more detail, right? So reference bit in some ways tells you that the page is recently used. It's set to 1 when the page is read or write. And normally what the OS does is it defines a clock period. Okay? So it defines a clock period where the clock hands are moving, right? And it's basically a timer. Every clock period, the R bit for each page is reset. So you go in and you reset for every page. And the next time you come along and you swap something, you look at it. Okay. If the R bit is 0, it means the page is old. It was not used anytime in the recent time period. Right? The page is old, not used for some time, you can possibly throw it out. If the R bit is set, then the page is new. It was recently used in the time period since you last cleared it, which means you probably shouldn't throw it out. Okay. The modified bit indicates the page has been written to. The flag is reset when the page is saved to disk. When a page is removed from the physical memory, um, if uh, if the M bit is 1, it will be saved to the disk. It's high latency, right? So not only do you have to remove, if you want to rent this piece of storage or this 4 kilobyte block to someone else, then if you have to wait all the way for the person occupying the memory space to get out and write himself or her write the page back to disk, then it's going to be bad, right? Yeah, and so if it's on the other hand, if the M bit is 0, it means it's not dirty, and the data can just be dropped or abandoned or dropped on the floor without being saved to the disk. And so this gets higher priority um, than the if the modified bit is set. So if the modified bit is unset, then it gets higher priority. So you can throw the page off and it gets higher priority on the system. Okay. So the page table entry helps us implement demand paging. So on an absent page table entry, which is a page fault, you choose an old page, write back if necessary, change this page table entry, load the new page into disk, update the page table entry, and restart the thread. So this is kind of the set of steps that you follow when on a page fault, right? And TLB will be automatically loaded because when the thread continues, and while pulling off pages from the disk, the OS runs another process. But remember that if there's no space and the OS needs to replace something, um, that replacement is going to take a certain amount of time. And so in such cases, the incoming page has to wait for the replacement to finish. Right. So here's a pictorial description of the steps in handling a page fault. So the word starts here. So I have a read, and the first step is I'm going to try to reference it, look at the page table. It's obviously possibly in this case on the disk. So I trap, and then what the OS does is move it from the backing disk into memory. In this case, it assumes there's space. If there's no space, then that is, if there's no free frame, then one of these guys would have to be removed. And step 3 really has to wait for step 2.5, the replacement to take place. So this is why the replacement is on the critical path and is expensive. And you reset the page table once the page is loaded, update the page table entry, and then you restart. So there are a number of page replacement algorithms. We'll go through them. I'll talk about which ones are used in the operating system.